Hello students, welcome to the EPG Pathshala. I am Ashok Goel from the Department of Physics and Astrophysics, University of Delhi. Today we are going to discuss about a module, Schur's lemma and orthogonality theorem from the paper Mathematical Physics. So students, let us see what we are going to learn in this module. In this module, you will learn important theorems or representations which enable us to check whether a given representation is irreducible or not. So we have already discussed reducible and irreducible representations. Now, how to find whether a given representation is irreducible or not, then the Schur's lemma is important in determining that. And through the use of orthogonality theorem, you will be able to know about the number and dimensions of irreducible representations of a finite group. That is, given a finite group, how many representation does it have will be determined by the application of the orthogonality theorem. One of the most important theorem in the study of irreversible representations is Schur's lemma. There are two lemmas, and then there is the orthogonality theorem of representations. Schur's first lemma is a way to check whether a representation is reducible or not. The second lemma is generalized to different irreducible representation of a symmetric group. And what is orthogonality theorem? The orthogonality theorem deals with the relationship between the matrix elements of different representations. Let us start with Schur's first lemma. The lemma says that any matrix which commutes with all the irreducible matrix representation is a multiple of identity matrix. In other words, if we can find a matrix M which is not a multiple of identity matrix, and if it commutes with all matrix representations d alpha of AR for every group element AR belonging to the group G, then d alpha AR is not an irreducible representation. That is, the matrix that can commute with a representation and is a multiple of identity, only then the representation is irreducible. I will now indicate the proof of Schur's first lemma. Let's assume there exists a matrix M such that it commutes with the representation matrix D of AR. That is, MD AR is equal to D AR M for all elements AR belonging to the group G. Taking the Hermitian conjugate of the above, we get D dagger AR M dagger is equal to M dagger D dagger AR. Since we have shown already in the previous module that dA can always be taken to be unitary, so we can multiply this equation on the left by dA. So the left side becomes dAR D dagger AR M dagger, and since D is unitary, D dagger is equal to 1, therefore M dagger is equal to dAR M dagger dAR, and therefore M dagger dA is equal to dAR M dagger, which means that not only M commutes with the representative matrix D, but M dagger also commutes with dA, and therefore the combination M plus M dagger as well as I times M minus M dagger also commute with dA. But note that M plus M dagger and I times M minus M dagger are Hermitian. So what we have learned? We have learned that we only have to consider the case when M is Hermitian. Now the matrix M can be diagonalized by unitary matrix U. That is, M is equal to U D U dagger, where D is a diagonal matrix. Let's define D bar A is equal to U dagger D U, and then we multiply this from the left by U inverse and from the right by U. When we do that, the left hand side is U inverse M DARU, which is equal to U inverse DAR-MU, which can also be written as U inverse M by introducing UU dagger between the matrix M and D. It can be written as U inverse M U U inverse D of AR into U. And now U inverse MU is D, that is the diagonal matrix D. And U inverse DARU is equal to U dagger DARU, which is D bar. Therefore, the left hand side is simply equal to D times D bar of AR, that is a diagonal matrix, times this new matrix we have defined as D bar of AR. Likewise, the right hand side becomes U1 D AR U inverse M of U, which is nothing but the matrix D bar A into D. So in terms of, so what we have obtained? We have obtained that the diagonal matrix D also commutes with the D bar matrix. And writing this in terms of the matrix elements, we have sigma over beta, D alpha beta, D bar beta alpha is equal to sigma over beta, D bar alpha beta, D beta alpha. The matrix D being diagonal, D alpha beta is simply equal to D alpha delta alpha beta. Therefore, D alpha D bar AR alpha gamma is equal to D bar AR alpha gamma DR. Therefore, D alpha minus D gamma multiplied by D bar AR alpha gamma is equal to 0. What does it tell us? Tell us that if the element D alpha is equal to D gamma of the diagonal matrix, then D bar AR alpha gamma is equal to 0, which means that if the diagonal element D alpha alpha of the matrix D are all different, then off-diagonal elements of D bar are all 0. And hence in this case, D bar A alpha are all diagonal and hence all reducible. The only possible off-diagonal elements of the matrix D bar can arise when some diagonal elements D alpha alphas are equal. For example, if D11 is equal to D22, then D bar of AR 1, 2, that is first row second column element of the matrix D bar AR can be non-zero. Thus, D bar AR can be put in the diagonal form. Thus, if D, which is a diagonal matrix, has entries like D1, D1, D1 up to some number n, and then D2, D2, etc. up to some number m, and so on and so forth, then, as we have seen earlier, D bar can be written in the block diagonal forms D1, 0, 0, D2. And this is true for every matrix in the representation. Thus, all representation matrices are in the block diagonal form. But if DAR is irreducible, which means that not all matrices can be brought into the block diagonal form, then all the D's have to be equal, which means that the matrix, the diagonal matrix D is nothing but unit matrix, that is D is equal to Ci, which means that the matrix M is equal to U, D, U dagger, and a diagonal matrix with D being a unit matrix commutes with all matrices. Therefore, this is equal to D, which is equal to Ci. And therefore, this matrix D is a unit matrix. There are certain corollaries which follow from the Schur's lemma. Number one, if you have a matrix M which commutes with the representation D for the group element AR, such that DARM is equal to MDAR holds for all M which are not equal to the unit matrix or a multiple of that, then DA is reducible. Number two, all irreducible representations of abelian group are one-dimensional. That's an important corollary. It says that if you have an abelian group, then all its irreducible as representations are of one dimension. To see this, let AR belongs to the group is an arbitrary but fixed element. If the group is abelian, therefore AR AS is equal to AS AR. So if DA is the corresponding representation of the group, then this implies that the matrices also are abelian, that is DAR, DAS is equal to DAS, DAR for all A's belonging to the group G. Therefore, by Schur's first lemma, DAR must be a multiple of the unit matrix. Why? Because they commute among themselves, and therefore for all elements of the group. Therefore, D itself must be a multiple of unit matrix C with 1, 1, 1 in the diagonal element. Let the representation DR is equal to C. So D is a multiple of unit matrix. Then it is an irreducible representation and is of dimension 1. Suppose we have two irreducible representations, D1 of dimension L1 and D2 of dimension L2. Then let a L1 cross L2 matrix M such that the matrix M commutes in such a way that D1 AR M, that is product of the representation D1 with M, is the product of the matrix M representation D2 for all elements belonging to the group G. If the representation D1 AR and D2 AR are inequivalent, then by Schur's lemma M is equal to 0. On the other hand, if D1 AR and D2 AR are equivalent, then D2 AR can be obtained from D1 AR by a similarity transformation. This D2 AR is equal to some matrix X inverse DA AR X for a non-singular matrix X, and in which case the matrix M is some constant times this matrix X. We will now indicate the proof of the Schur's second lemma. Let us start with two matrices D1 and D2 and a matrix M such that D1 AR M is equal to M D2 AR for all elements of AR belonging to G. Taking the Hermitian conjugate of this, we get M dagger D1 dagger AR is equal to D2 dagger of AR into M dagger. But D dagger of AR is equal to D inverse of AR because any representative matrix can be considered to be unitary, and since the representative matrices satisfy the same group multiplications as the elements themselves, so D inverse of AR, which we have seen earlier also, is D of the inverse of the element. Therefore, M dagger D1 of the inverse of the element AR is equal to D2 of the inverse of the element AR into M dagger. Multiplying this by M on the left, we get MM dagger D1 AR inverse is equal to M D2 AR inverse M dagger. Therefore, MM dagger D1 AR inverse is equal to D1 AR inverse MM dagger for all A inverse belonging to the group G. Therefore, by the Schur's first lemma, MN dagger is equal to Ci is a square matrix. Since we have considered two representative matrices D1 of order N1 and D2 of order N2, and from the first lemma, we have seen that mm dagger is equal to C times a unit matrix. Therefore, dagger is a square matrix. Now let us consider a few cases separately. Let the dimensions of the two representations equal, n1 is equal to n2. That means if C is not equal to 0, then determinant m is not equal to 0 and m has an inverse, because dagger is equal to Ci and we have assumed that n1 is equal to n2. If C is not equal to 0, then the determinant m is obviously not equal to 0 and therefore m has a inverse. Therefore, m inverse d1 ARM is equal to m inverse m d2 AR, because m1 ARM is equal to m d2 AR. Therefore, m inverse d1 of ARM is equal to m inverse m d2 AR, which is equal to d2 of AR, which implies that d1 AR and d2 AR are equivalent for all elements AR belonging to G, because D2 can be obtained from D1 by a similarity transformation with the matrix M, which is contrary to the assumption. Therefore, C is equal to 0 and dagger is equal to 0, which means that in terms of elements, M alpha beta, M beta alpha dagger is equal to M alpha beta star, because the matrix element of a unitary matrix are obtained by interchanging the rows and columns and taking the complex conjugate. Therefore, M alpha beta, M dagger beta alpha, sum over all beta is equal to M alpha beta modulus square sum over B, which is equal to 0 for all alpha, and therefore M has to be equal to 0. Now we consider the case when the dimension of the irreducible representations are not equal. That is, n1 is not equal to n2. Therefore, in this case, M is a n1 cross n2 rectangular matrix having n1 rows and n2 columns. Let n2 be greater than n1. We can construct a square matrix M prime by adding to this matrix M n2 minus n1 zeros. That is, M prime can be written as M and a matrix 0 such that M prime dagger becomes a row matrix M dagger and 0. Now, M prime dagger M prime is M dagger 0, which is a row matrix, multiplied by M0, which is a column matrix, which becomes M dagger M, which is equal to a constant times the unit matrix by Schur's first lemma. So, where I is a n1 into n2 unit matrix. However, by construction, determinant M prime is equal to 0, which will obviously implies that C is equal to 0, since M prime dagger M prime is equal to M dagger M. Determinant M prime dagger M prime is equal to determinant M dagger M, and therefore M prime is equal to 0. Identically, this completes the proof of the Schur's second lemma. We will now state a very important theorem which we mentioned earlier, which is great orthogonality theorem. And what does the theorem say? It says that if G is a group of order n, that is, it has n elements, E, the identity, then A2, A3, An. Then D alpha A and D beta A be two inequivalent irreducible representations of dimension L alpha and L beta respectively. That is, we first have a group of order n, then we consider two irreducible inequivalent representations of dimension L alpha and L beta respectively. Then the great orthogonality theorem states that if we take the product of these two representations, D alpha Ij D beta KL for the both being representation of a particular um, group element, and sum over all the group elements from 1 to n, then this is equal to n by L alpha, delta alpha beta, delta ik, delta jl, which means that this product is non-zero only if the representations are the same. And again, if they are of the same dimension. So this relationship helps us in determining whether the representation is irreducible and how many irreducible representations there are for a given group representation. I will now prove the great orthogonality theorem. Let us start by constructing a matrix M given by M is equal to sum of d alpha A alpha into X into d beta A alpha inverse, where d alpha A alpha is the representative matrix for the group A alpha, which has the dimension L alpha, and d beta A alpha inverse is the representative matrix of dimension L beta for the element A alpha inverse, and X is any arbitrary L alpha cross L beta matrix, and the sum is taken over all group elements. So D alpha is a representative matrix of order L alpha, D beta is a representative matrix or representation matrix of the inverse of the same element, which is of order L beta. Multiplying this expression, M is equal to sigma D alpha AR X into D beta A inverse by the representation matrices, we get D alpha AB of M is equal to sigma over A D alpha AB D alpha AA X times D beta A inverse into D beta AB inverse D beta AB, because D beta AB inverse into D beta AB is unity, so I can just multiply it with that, which gives me that D alpha of AB times M is equal to sigma, that is sum over all elements, D alpha of AB AA multiplied by the matrix X multiplied by the matrix D beta for the element AA inverse AB inverse, which also is an element in the group, times the matrix D beta of A beta, which then means that D alpha of AB multiplied by M is equal to M times D beta of same element AB. Now let us consider the two cases separately. The case one is when alpha is equal to beta, then the matrix M is equal to 0 by Schur's lemma, but the matrix M is therefore given by sum over all the group elements of D alpha ij AA X times xjk into D beta KL of AA inverse, which is equal to D alpha ij AA xjk dB star KL AA, because of the fact that the matrix D is a unitary matrix. And as I said before, the component or one element of the unitary matrix are obtained by taking the complex conjugate and changing the rows into columns. Now, X is an arbitrary matrix. So let us choose X such that all its elements are 0, except the Rth element, which we take to be unity. Therefore, Xjk is equal to delta Jr delta Ks. That is, only unless J is equal to R and K is equal to S, all the other elements of this matrix, which is an arbitrary matrix, are 0. We then have sum over all the elements of D alpha ij AA, delta JR, delta KS, D beta star LK. That is, we are just replacing the matrix X by delta JR, delta KS, and this expression then becomes equal to 0. What does it mean? It means that for different irreducible representations, the product of the IR element of the representation D alpha with the complex conjugate of the matrix element LS of the matrix D beta, sum over all group elements is 0. Let us now consider the second case, which means two representations are the same, that is alpha is equal to beta. We then have M is equal to sum over all the group elements D alpha AA X times D alpha AA inverse, which implies that D alpha into M is equal to M into D alpha, which means since D alpha is an irreducible representation by Schur's lemma, it implies the matrix M is a multiple of the unit matrix I. Now trace of M is equal to sigma sum over all elements trace of D alpha AR X D alpha A inverse, which is equal to, now what is the trace of M? M is C times a unit matrix. So trace of M is C times the dimension of the unit matrix, which is equal to L alpha. So therefore trace of M is equal to C times L alpha, which is equal to trace of D alpha of A inverse D alpha AAX, which in turn is equal to the trace of D alpha A alpha inverse X D alpha AAX. Therefore trace of M is equal to trace of X is equal to n times the trace of X. Therefore C is equal to the constant C, where M is equal to Ci. This constant C is n times the trace of X divided by L alpha, where L alpha is the dimensionality of the irreducible representation and n is the order of the group. Now trace X is equal to Xjj, which is equal to delta Jr, delta Js is equal to delta Rs. Therefore, and C is equal to n times delta Rs by L alpha. We therefore get summation over all group elements belonging to the group G, the product of the matrix components D alpha IR of AA into D alpha star of IS AA is equal to n divided by L alpha delta IL delta Rs. This gives us the orthogonality between different matrix elements within a given irreducible representation, because D alpha star are the matrix elements of the same representation D alpha. So it tells us that the product of the matrix elements of the matrix D alpha and the complex conjugate is given by this expression n by L alpha delta IL delta Rs. So it gives us the orthogonality between different matrix elements within a given irreducible representation. We then finally get the great orthogonality theorem for the irreducible representation of the group, namely the sum of matrix elements of irreducible representation of dimension L alpha of the group of order n satisfy the following orthogonality relation, namely summation over all the elements of the group of D alpha IR AA multiplied by D alpha star IS of AA is n by L alpha delta IL delta Rs, which then becomes alpha sum over all the elements D alpha AR IR D beta star AA LS. That is, if two representations of different dimensionality alpha and beta, then they are orthogonal, and the final relation is that D alpha AA IR multiplied with d beta star A, L, S, sum over all the group elements from 1 to n, where n is the order of the group, is equal to the order of the group divided by the dimension of the representation, with the condition that the two representations have to be equal, otherwise this product is 0. So delta alpha beta represents that. Delta IL says that the element rth element of the representation d alpha is to be multiplied by the ith representation of the element d beta star, what is meant by the expression delta IL, and similarly delta RS. So the final expression for the great orthogonality theorem is that sum over all group elements d alpha AA IR and d beta star AA LS is equal to n by L alpha delta IL delta RS delta AB. Yeah, the theorem has an elegant interpretation in vector space. For example, consider an n-dimensional complex vector space in which the axes are labeled by the group elements. And what are the group elements? Group elements are E, A1, AN, for all A's belonging to G. And this is called now the group element space. Now consider a vector in this space formed by the components of the matrix elements of a irreducible matrix D alpha A, whose components are I and J. So how many components are there of the matrix? Since the dimensionality of the matrix is L alpha, so its number of components is L alpha square. Thus each vector in this group space is labeled by three indices I, J and alpha, where alpha refers to the dimensionality of the representation. I and J are the corresponding elements of the matrix of representation for a particular group element A. Then the vector in this space can be defined as a vector d mu A I J specified by three indices mu I and J, and its components being d mu I J for the element E, that is the ijth element of the irreducible representation d mu for the group element E, and likewise for the group elements. So its components of this vector d mu ij A are d mu ij E, d mu ij A2 up to d mu ij AN. Now the great orthogonality theorem says that these vectors are orthogonal to each other. So there are a total of L mu square sum over all the representation mu n-dimensional vector. So in all, how many vectors are there? L mu square for each irreducible representation. As a result, sigma L mu square sum over all the representation has to be less than or equal to the number of elements in the group or the order of the group. Because there cannot be more than n naturally perpendicular independent vectors in the n-dimensional space. That's why this number has to be less than n. Suppose we have a finite group consisting of 6 elements, a group, symmetry group S3, or for example, or a group D3 of the symmetry of a regular triangle. How many irreducible representations can it have? And what are the dimensionality of this irreducible representation? That can now be easily determined from the theorem, because it says that n, the total number of elements in the group, is greater than or equal to the sum of the squares of the dimensionality of the irreducible representations. That means L1 square plus L2 square plus L3 square is less than or equal to 6. And the only solution for that is L1 is equal to 1, L2 is equal to 1, and L3 is equal to 2, which means that it has two one-dimensional and one two-dimensional irreducible representation. We have defined the character of a representation. The matrix representations of a group are not unique. They depend on the choice of the basis vectors, and you can go from one representation to another by a similarity transformation. But however, the trace of a matrix, however, is invariant under a similarity transformation, because if you have a matrix D which can be obtained from the matrix S by similarity transformation, that is the matrix D is equal to S inverse AS, then the trace of D is trace of any S inverse AS, which is by using that property of the trace, that the trace of a product of matrices taken in a cyclic way remains the same. Therefore, trace S inverse AS is trace S inverse SAS is equal to trace S. Thus, the trace of all matrices of representation would uniquely characterize a representation, and this is called the character of the representation. Now, there are some useful properties which follow from the character of the representations. The first property is this, that if representation d alpha A and d beta A are equivalent, then their characters are equal. That is, chi alpha A is equal to chi beta A for all elements A belonging to group G. Secondly, if two group elements A and B are in the same class, what does it mean? It means that there exists an element C belonging to G such that C A C inverse is equal to B. One element can be obtained from the other element by a similarity transformation. If we take the trace of this, then since trace of C A C inverse is equal to trace B, but trace of any number of matrices is the same when you permute the matrix in a cyclic order. So trace C A C inverse is trace C inverse C A, which is trace A. Therefore, trace A is equal to trace B. Therefore, the character of chi alpha for the group element A is the character of for the group element B, which belong to the same class. That is, elements belonging to the same class have the same character. That is, X alpha, the character is a function of a class and not of each element. So let us denote chi I as chi of Ci, where Ci is the character of the ith class. Let Nc be the number of classes in the group G, and Ni is the number of elements in the class C. So a class C has a number of elements, and there are number of classes in the group G. Nc is the number of classes in the group G, and Ni is the number of elements in the class C. Remember that the identity element E is a class by itself, and it has only one element. Therefore, sigma Ni is equal to N. Now, from the great orthogonality theorem, d alpha ij of the element A multiplied by d beta star of element KL of the A sum over all the group elements A is equal to N by L alpha delta alpha beta delta Ik delta JL. Taking the trace of this, we get chi alpha A, chi beta star A sum over all group elements is equal to N by L alpha delta AB delta Ik delta Ik, which is equal to N by L alpha delta AB delta N by L alpha delta A alpha beta and delta II, which is equal to N times delta alpha beta, or in other words, Ni times the character of the ith class of the representation d alpha multiplied by chi I star b, that is the character of the ith class in the representation beta sum over all elements on that class is equal to N times delta alpha beta. This is the gate orthogonality theorem for the characters. We will now discuss something which tells us about the dimensionality of the irreducible representations. Let us define ui alpha is equal to under root ni by n chi alpha ci. That is, ui alpha is the character of the ith class in the representation alpha multiplied by the number of elements in the class divided by total number of or the order of the group, and under root of that is taken. So having defined uia in this manner, then the gate orthogonality theorem implies ui alpha, ui beta star, sum over all the classes I is equal to 1 to nc is equal to delta alpha beta. Thus, if we consider ui alpha as components in nc dimensional vector space, then the vector u alpha consisting of the vector components of the vector being u alpha 1, u alpha 2, u alpha nc. That is, the dimension of the vector space equals to the number of classes in the group G. We have one such independent basis function for each irreducible representation of the group. Then the vector u alpha defined for alpha is equal to 1, 2, nr, where nr is the number of independent irreducible representation. So nr is the number of independent irreducible representation of the group G, which has a number of classes equal to nc in it. Then we have one such independent basis function for each irreducible representation of the group, and the vector u alpha has components for alpha is equal to 1, 2, nr, where nr is the number of independent irreducible representation, and these vectors form an orthogonal set of vectors. That is, u alpha, a scalar product of two vectors u alpha and u beta, which is given by the product of the components of the vector for the representation alpha and beta, namely u alpha I, u beta star I, sum over all I is the number of classes from 1 to nc. This is equal to delta alpha beta, which means that nr is less than or equal to nc. That is, the number of irreducible representation is smaller than or at most equal to the number of classes of G. In fact, it is equality that holds. Thus, this theorem greatly restricts the number of irreducible representations. Now I discuss a criteria for irreducibility which is of great use in the applications and in deciding whether a given representation is reducible or irreducible. Let D alpha, where alpha is equal to 1 to nr, are all inequivalent irreducible representations, then any representation D can be decomposed in terms of these irreducible representations, that any representation D can be written as irreducible representations as C alpha D alpha sum over all alpha, where C alpha is an integer and it gives us the number of times an irreducible representation D alpha appears in any general representation D. In terms of traces, that means the trace chi, which is the character, trace is the character, chi of Ci is equal to C alpha D alpha of Ci, where Ci is the ith class in the representation. Multiplying this by Ni chi beta Ci star and summing over all the classes, so I have Ni chi Cr star is equal to sigma over I from going from 1 to nc, where n is the number of classes, and another summation going from alpha is equal to 1 to nr, C alpha Ci chi beta star Ci Ni. So now, from the orthogonality of the characters, this can be written as sum over alpha C alpha delta alpha beta n. Therefore, C alpha is equal to 1 upon n, sigma over I from 1 to nc is the number of classes, into ni is the number of elements in the class, multiplied with the character chi of the class Ci and the character C alpha star of Ci. Manipulating these, we then get sigma ni chi I star is equal to sigma ni sigma over alpha and beta C alpha chi I alpha C beta chi I beta star, which is can be written as sum over n C alpha star. And this leads to the theorem. And what is that? That if the representation D with character chi I satisfies the relation that ni chi I star sum over all I, where I is the number of elements in a particular class, is equal to n, the order of the group, then the representation is irreducible. So finally, let us summarize what we have learned so far in this module. Number one, if there exists a matrix M which is not a multiple of identity matrix, and if it commutes with all matrix representations D alpha of AR for all group elements AR belonging to G, then the representation D alpha AR is not an irreducible representation. It is an irreducible representation if and only if the matrix that commutes with it is an identity matrix or its multiple. Next, the orthogonality theorem of matrix elements of two group representations, say D alpha, D beta, for the same group element A, says that sigma D alpha A ij D beta A KL is equal to n upon L alpha delta alpha beta delta I K delta JL, which means that there is an orthogonality between the different representations of different dimensions, and then there is an orthogonality between the components. In terms of the character, this says that the sum of the character for the given element A chi alpha A chi beta star A, that is the sum of the character for each element of the representation A multiplied by the character of the same element in the representation B, then its complex conjugate. This sum of the characters is equal to n times delta alpha beta. Then there is an orthogonality theorem of classes, which says that ni is the number of elements in the ith class. Ni multiplied by xi alpha star xi beta is equal to n alpha beta for all alpha beta, for alpha beta is equal to 1, 2, etc. This restricts the number of irreducible representations by this expression, which says that sigma L alpha square is equal to n, where alpha is summed over all the classes. So restricting the value of the characters, so we have ni x alpha square sum over alpha is equal to n, and the criteria for irreducible representation with character chi I. So if chi I is the character of the representation should satisfy if that sigma ni chi I chi star is equal to total number n.